Okay, last time we have seen how we can make maybe a stable multivibrator with two different techniques. And today we'll see one other type of device. In fact, it's called square wave generator. I mean, square wave generator is again a similar concept, like how to make a circuit which will be generating a signal Vy, a repeating signal. So this repeating signal can be obtained with this what is called Schmitt trigger circuit. So we have analyzed this circuit before, this circuit, and then we know that the response of the circuit is like this. So when we keep increasing this Vin increases, you know, Vy, V1 is going to be 1. And then when we increase this until a certain value, this MV1 value, the signal will be, output will be V1, but then it will be going dropping, and then it will go like this. But on the way back, when the signal is coming backwards, so it will be going back this way. So we learned about this, so I'm not going to repeat this again, how to obtain this graphic. But if you take the output Vy and then connect to the input with a resistor and then put a capacitor in the input, then we will see that there will be repeating signal, and the output will be switching between high and low as an maybe asynchronous circuit. So here, in order to find what is happening with the circuit, we can, the best way for analyzing these kind of circuit is to assume that the capacitor is discharged initially. So if the capacitor is discharged initially, the voltage here is going to be 0 volt, right? So if the input is 0, output can be either here or here or here, if you remember. So this point, the midpoint, 0 point, is origin is the point where the state is unstable. So we don't think that this will be the case. So we assume, let's say, output to be maybe V1. Okay, so at t is equal to 0 plus, we will assume that the voltage here is 0 Vin, and then output Vy is going to be V1. So what happens in that case? Output is V1, and you know that the current through here is equal to 0, because these are supposed to be CMOS elements, or ideal op-amp, or comparator. So the current is equal to 0. So that means the impedance here, input impedance, is infinity. Okay. So this is important. So if the output voltage is V1, the capacitor is going to be charging in that cycle. So this is V1, let's say V1, and then this is 0 volt initially. We see 0 plus is equal to 0 volt. So the current is going to be coming and charging this capacitor through that resistor. And that means the signal will try to target to reach to a value, right? So this value maybe is going to be like this, but then it will try to go to the target of this thing is V1. So that's what capacitor is trying to reach to. And then capacitor meaning reaching to that means, you know, this voltage is trying to increase. So Vn is increasing, but there's going to be a change when the capacitor reaches to MV1. So this value of MV1 is the point where after this, the signal will switch to minus V1. So up to here, the capacitor will be remaining at V1, okay? And then the goal of the capacitor is to charge to V1, but at MV1, the signal will change. And so that happens, let's say at T1 time. So after this, what will happen? The signal, output signal, will drop to minus V1. So when it reaches to minus V1, we can change the color and then say that then it reaches to minus V1. Okay, so it goes to minus V1. So this will be minus V1 now. Maybe I should change the color here to this color. It will be dropping. Okay. So as soon as this drops to minus V1, the characteristic will be again changing. Now the signal is going to be minus V1. Okay, so when is this going to be minus V1? When, you know, Vy at T1 plus time. So, so what is the value of the capacitor? MV1. And what is the target of capacitor then? It's going to be trying to reach to the goal is trying to reach to minus V1 this time, okay? So the capacitor will be discharged, and then when it reaches to, so this signal is coming like this, when it reaches to minus MV1, then the signal will switch to V1 again. So then, you know, when it reaches here, the signal will reach to V1 again. So that value, let's make it with maybe this color. It will be like this, okay? So now it's here. So since output is V1, the capacitor goal is going to be trying to reach to V1 again. And then it will be going like this. Okay. But then the signal will be switched again when this reaches to MV1. Sorry, maybe I should do it like this. So the goal is to go to V1, but it cannot, so it will be switching again. So when it switches to here, the signal will be going to minus V1. So maybe minus V1, let's put it this color. And then, so it will be going like this now. Okay. So this will keep repeating itself. And then this will try to go to minus V1 again. But then when it reaches to here, things will change. So, so we can determine the time difference here between this time and this time should be equal to each other. This one maybe is not. So the time difference here is going to be maybe different because the signal goes from 0 to M1. But in the other ones, it's the same thing. So if we look at the tau, this will have a tau, and then this tau will be equal to this tau because the capacitor is charging and discharging through the same resistor. Okay, so if this is capacitor, then the tau is going to be equal to R times C. So tau is same, and if we calculate this difference, T2 minus T1, that should be equal to this T3 minus T1, okay? So T2 should be equal to T3 minus T1. That should be equal to T divided by 2. And because if we call this thing time of T, and then we can find the frequency of operation, and F is going to be 1 over T. So we can find the clock frequency here. How can we find that value? The way that we find it is by writing the capacitance equations here. So if the you know, we need to look at this at this time. Let's say when T is equal to T1 plus, okay? So at this time, we know that Vy T1 plus is equal to minus V1, okay? And then Vy infinity is, the target is to make it what? Minus V1. So it starts from here. Did I make a mistake? I think I made a mistake. Okay, yeah, no, this is correct. So what about Vc of T1 plus, and that is equal to M V1. So the capacitor voltage here is MV1. So we can, write the equation according to, and we can find T1, we can find T2, and then, calculate it. But we don't really need to do that. In that period of time, we can write the capacitor equation. Vc of T in this period is going to be equal to V final plus V initial minus V final e to the power minus T minus T1 divided by tau. Okay. So because the timing, we started from T1. So this is the time period for T larger than T1. That's going to be the capacitor voltage equation. So when T reaches to T2, okay, so we know that V final is equal to -1, V1. Initial is equal to MV1. And the final is minus V1. So therefore, when Vc is equal to T2, that's what we want. And that's the value where voltage becomes minus MV1. Then I can write the equation here, minus V1 plus MV1 minus V1. So it becomes plus e to the power minus T2 minus T1 divided by tau. So from here, I can find that T2 minus T1 is going to be equal to R times C, which is tau, times ln 1 plus m divided by 1 minus m. Okay, you can verify that this is the case. So therefore, we can obtain, this is the result, T1, okay. So if you want to write, let me erase this one, because this already explained. If you look at T2 or T3 minus T2, it's going to be equal to T2 minus T1. And then we can find T to be 2 times R times C times ln 1 plus m minus 1 minus m. And therefore, F is going to be equal to 1 over T. And this is how we can find the clock period. So we created a square wave signal, but this time the voltage is switching between V1 and minus V1. Okay, so V1 and minus V1, but we can obtain it. So here, the only thing maybe I can just get your attention is that in this device, the signal will go from here to here to here to here to here to here to here. So it will be making a circle around that square, and that's how the device operates. So note that M was found before. So for this circuit, Okay, so we don't need to really calculate it again. So here, just to note to you that we started by this assumption, and then we noticed that the circuit will be making repetition. And found. So T1 is not important. Maybe I should write it here. Determining T1 is not critical. Okay, so we had to start from somewhere with one assumption. So that's what we did. And so it was more important. T2 minus T1, which is equal to T3 minus T2, are more important. So that's what we can do to determine this square wave generator. I guess there's one extra slide here, which we really don't need to, cover again. It's already covered, but we started from here, and then we noticed that this goes like that, and then it goes back to here, and then switches here. That's how, operation continues. Any questions? No? Okay. There's one more interesting circuit, triangular wave generator. So if you want to obtain a triangular wave, we can use again this Schmidt trigger. Okay. But this time we can make the Schmidt trigger non-inverting. So it starts from here, and then it goes up, and then it goes like this, and then on the way back it comes like this. Okay, so circuit wise this is possible. Just one more block you add it up, and that's what happens. So if you combine this with another circuit, and this is an integrator. I don't know if you know about this, but this is an integrator. Okay. So then we can, again, the input impedance here is infinity. We can get a triangular wave signal. So how can we do this? We need to look at the signals again. Here we didn't mention, but this is M times V1, and this one is minus M times V1. Okay, what is V1? V1 is this voltage, or we can call it VCC, I guess. This time it's minus VCC plus VCC. So therefore, maybe I should call this thing VCC, and then this should be VCC. Okay, so V1 is equal to VCC. And we have an ideal op amp in there with a gain of infinity. and there's a capacitor. So what is happening with this circuit? Here, we will again assume that output V2 starts with something, okay? It's going to be either VCC or minus VCC. We can start with assuming that, assume that VC is initially 0. That's typically what we do. And assume that V2 is VCC plus VCC, okay? So if V2 is plus VCC, we can maybe start like this again. This is VCC. And then check what is happening with this circuit. So if V2 is VCC, okay, sorry, I mean, this maybe is confusing because V1 is not here anymore. So there's V1 also here. So we don't want this V1 to be confusing ourselves. So that's why I erased it. So V2 is VCC. The capacitor is 0. So V1 is 0. So input is 0 initially. Or sorry, maybe I should do it like this. So we are here, okay, initially. And input is 0, output is VCC. Why input is 0? Because we assume that this is at 0 plus is equal to 0 volt. So if that's 0 volt, because of the gain of infinity, you know, this signal V in minus of the op amp, V plus of the op amp is equal to V minus of the op amp. Okay, so we can say this is V plus, this is V minus. So, or V plus, V minus maybe is better to write. So because of the gain of the op amp, we know that output is going to be, or two inputs will be equal to each other. And since this is 0 volt, then at, I mean, here, V minus is always going to be 0 volt, okay? V minus is going to be equal to always V plus because of the op amp. Response. So therefore, when we say V1 at 0 plus is going to be equal to V minus plus or minus VC. Capacitor of the capacitor is defined like this. VC of 0 plus, okay? So VC of 0 plus is 0. This is always 0, always. And then this one is initially. So V1 of 0 plus is equal to 0 volts. So initially, V1 is 0. So that's, we assume that V out is plus. So the capacitor voltage is initially here, and then V1 is initially 0. That's how we start the analysis. So here, we know that due to that V2, okay, so this is V2 voltage, V2 is VCC. Therefore, there's going to be a current here, okay, so there's going to be current here. So that current will be a fixed current. So IR at 0 plus is going to be equal to V2 0 plus divided by R. Actually, V2 0 plus minus V minus, which is 0 anyway, 0 volt. So therefore, it's going to be V2 0 plus divided by R. What is V2 0 plus? Here it is VCC. So VCC divided by R is going to be constant current through the resistor. So where does that current go? It cannot go to the op-amp because we know that op-amp is ideal op-amp, so it doesn't get any current. So all the current will go through this. Okay, so this current will be equal to capacitor current. So what happens if there's a capacitance constant current through the capacitor? Capacitor will start charging. So the capacitor will start charging. Okay, because of the definition of the sign here plus, so capacitor will be increasing. So the capacitor will be increasing, and that means, in fact, V1, which is equal to, note that V1 is equal to minus VC. Why? Because V1 is equal to this one, V1 minus, which is equal to 0, minus VC. So therefore, maybe I should, write it more formally here. V minus VC of t, which is equal to V1 of t is equal to minus VC of t. So therefore, when the signal, goes up here, and this is going up, here this will be going down, V1. So V1 becomes negative. Okay. So V1 goes to this direction in the table. So when this reaches to minus M, VCC is the critical point, and output will be changing. So that means, when the capacitor becomes MVCC, this happens. Okay, so when the capacitor becomes MVCC, that happens. So what happens then? The signal will be switching. So V2 becomes, after that point, V2 becomes minus VCC. So so if V2 switches to minus VCC, then the current direction changes. Okay, so IR at T1 plus, maybe I should do this a little bit later here. IR, or maybe I should write it here. IR when T is equal to T1 plus becomes, again, V2 of T1 plus divided by R, because this is always 0. And V2, that becomes minus VCC over R, because this switches to here now. So the current through here becomes negative. And that changes the whole story here for the capacitor. Capacitor will start then discharging. And it will be discharging. So then accordingly, this will be charging. So this will be charging. So this will be now going this way. And when it reaches to MVCC plus MVCC, things will be different. So that means the critical thing here is minus MVCC because they are negative this time, negative of each other. And when this happens, things will change again. And then this will be going back to VCC. And then this will start charging. And then when this starts charging, this will start discharging. And things will again change. So when we look at V2 is square wave. Signal, but V1 is triangular wave. Okay. So this is how we generate a triangular wave. So here we can also determine the clock frequency, and the clock frequency the first time is not that critical. This is T1, T2, T3. So this period is equal to this period, and then we can call it T divided by 2, and then this will be T divided by 2. So what is important thing is, again, T2 minus T1. And how can we determine this? What is T2 minus T1? So this is what we need to calculate. And then we know that this will be equal to T3 minus T2, and that will be equal to T divided by 2. So how can we calculate that? We can calculate that by looking at the current, which is charging the capacitor, and the amount of signal. Okay, so the charge, you know that the charge Q is equal to capacitance times delta V, which is equal to I, the current, I of R, or I of C, or I of R, which is equal to IRC, times delta T. Okay, delta T is equal to T divided by 2. Okay, so we calculated R before. I mean, we can look at the T1R, and that is this much. And the voltage is, and the capacitor is discharging, so it's going to be minus. So the capacitor times delta V, which is equal to minus MVCC minus plus MVCC. Okay, and that's the voltage change, because it's minus sign, minus, is equal to IR, which is here, this IR, minus VCC divided by R, times delta t, which is this one, delta t times delta t. And from here, we can determine delta t as, what is it? 2m 2m VCC divided by VCC times RC. Where that RC comes from, R is coming from here, C is coming from here. So therefore, delta VCCs are going to cancel, and then delta T will be equal to, maybe I can write it like this. Delta T is going to be equal to 2m times R times C. So that's how we can find T divided by 2. And of course, T will be 2 of these. T will be equal to 2 delta T. Therefore, it's going to be equal to 4 times M times R times C. So from here, we find the value of T, and the value of T determines here, gives us frequency of operation. And so F is equal to 1 over 4 MRC. So this is how we can obtain interesting signals, repeating signals, which are useful for digital domain. Okay. Do you have questions? Any questions? Okay, so we have seen that we can use, this block, square wave generator, with an interesting feedback, and then we can obtain maybe different type of circuit blocks generated with this. This includes maybe bistable multivibrator to make a square wave signal, or square wave generators, or astable circuits, or monostable circuits. So all these are possible with this maybe op-amp, and then kind of circuits. But in the market, some people saw this potential of these kind of circuits, and then created a very famous timer circuit. So this is an IC which can be used for maybe creating asynchronous circuits, or it can be created to make pulses oscillators, and all the things that we have seen in the past maybe can be generated with one chip. So this chip, has an input signal, VDD ground, and then output signal, of course. It has a reset signal, maybe trigger, discharge, and some input signals. Okay, so but what is inside, and then what can this do? So in order to understand and use this, we need to look at what is inside, and this is part of the course work. So this is not a very complicated circuit inside. In fact, what you have is maybe 3 resistors, which is dividing a supply voltage of VDD into 3 parts. So 1, 2, 3 resistor, and then a comparator. Okay, so it's like an op-amp, and then SR latch, RS latch, SR latch, and maybe a reset signal, which we don't really use it much. And then, there might be an output signal after power amplifier. So in this circuit, we will look at the operation, like what happens with this circuit. So, and then, pin wise, maybe this is pin 5, and then supply voltage pin 8, and then ground maybe pin 1, and then trigger is pin 2, and maybe threshold voltage is 6, and then reset is 4, and discharge is 7, and output is 3. Okay, all the inside is given like that. So we will look how we can obtain bistable multivibrator using this circuit. And when we do that, we will understand that what we have here with this kind of circuit is again a kind of Schmitt trigger. So depending on the signal, we can see the operation. So here for the proper operation, we will be connecting in this circuit. Maybe I should do it like this. Okay, the threshold voltage, if I connect this one, maybe I should select a different color to make it more clear to see. So if I connect this as Vn, and then the threshold voltage is connected to trigger voltage, okay, and then say that this is Vn, then we will notice that the operation is going to be very interesting. How is it going to be interesting? So if the input is 0, what happens if the input is 0? So we start, let's say, from here. Input is 0. So let's say this is Vn voltage. Okay. So if the input is 0, what happens to the output? So input is 0. what happens to here? I'll start maybe again doing the colors here. You know, I'll be differentiating things with the color. So input is 0 voltage-wise. Let's make it in a blue color. That's okay. So input is 0. Input is 0. What happens to the output? So here, when input is 0, what is S? What is R? You know, so these are, maybe we can write. You know, this S, when input is 0 or slightly larger than 0, is going to compare itself, this one, with this one, which is, let's say VDD is equal to 6 volts, okay? So just to make things, you know, easier to analyze. So if that's 6 volts, this is going to be 2 volts, this is going to be 4 volts, okay? So compared to 2 volts, when input is 0, S is going to be 1. So this is going to be high or logic 1. Okay, so when input, and that's going to be the case. What about the other one? Compared to this one, R. So what is the output of this thing? You know, the minus sign is 4 volt, the plus sign is 0. Therefore, R is going to be equal to 0, logic-wise. So if that's the case, our circuit will be set. Set means this will be 1 and this will be 0, okay? So, so therefore this will be 0, Q bar. And if that is the case, a amplifier output is going to be 0. So this is going to be the starting point. When we start increasing Vin, this is Vin, okay? So let's say Vin increases. When Vin increases, there's going to be a change when we reach to this point, okay? Let's say this is 2 volt, this is 4 volt, this is 6 volt. Okay? So what happens? What does change when input goes to beyond 2 volt? S will go to 0, correct? So R will remain at 0 because compared to 2 volt, again, this R is again going to be 0. So, and then what is Q bar? We know that Q n plus 1 bar is going to be equal to Q n bar. The data will store and then not change its value. So let's say this is 2 volt, this is 4 volt, and this is 6 volt, okay? So nothing will change in the circuit. So when we keep increasing input, after 2 volt, nothing will change because SR latch will keep its value, stored value. And until the input becomes beyond 4 volt, because if the input goes beyond 4 volt, then S will remain at 0, but R will go to 1, reset. Okay, so maybe I should select a different color there. So different color can be maybe red. Okay, or this one. So after this point, S becomes or remains 0, but R becomes 1. Why? Because now this is going to be compared to this is going to be maybe 4.1 volt. When we go to 4.1 volt, R becomes high. And R becomes high means reset. That means Q bar, I mean, this becomes 0, but then this becomes 1 or high voltage. If it becomes high, the amplifier output will give us a high voltage. So this voltage, high, output is going to be maybe VCC, okay? So this will be VCC, this will be VCC. So output switches to, or VDD, sorry. You know, after or beyond 4 volts, the output will switch to VDD. And then if you keep increasing this will be continuing like this. So this will jump up. Okay. Of course, we cannot go beyond maybe 6 volts. So this will be stopping here. Okay, now the voltage after this became like the color changed. Okay, so up to here, maybe it was like this, it was like this, and it switched. Okay, now we will be going backwards. When you start going backwards, what will happen? So there is no memory effect for this part of the circuit, no memory effect, but there is SR latch in there. So in the SR latch, let's start going backwards. Okay, so from here, we are here. And then we start going backwards. When we start going backwards, the signals will remain same. But here, the data, which will be storing its value, remember, this will be stored value. Here, it's going to be remaining at reset. Okay, so on the way back, this will remain at reset. So what does that mean? That means the signal down to here, it will be remaining at reset value. Okay, so on the way, this will be 1. Okay, while going up, it was 0. It was 0 going up. Like on the way back, it is remains 1. So therefore, it will be only changing when it reaches the 2 volt. So between here and here, this time it will remain high. Okay, output will remain high. And then after that, it will go to maybe again to 0. Okay, like this. So, I mean, we have the Schmitt trigger kind of response coming from the circuit. So we don't have a feedback mechanism here, but we obtained a similar non-inverting bistable multivibrator. Okay, so but this time it's non-inverting. What does that mean? You know, input is 0, output is 0, input is 5, output is 5, or 6. That's 6. So this is therefore a very useful device. Here, notice that we obtain this kind of graphic by doing connecting trigger to threshold and defining it as input Vin. So if we just put here at the output some resistors and capacitors, then we can obtain a multivibrator here. So that is done here. So instead of connecting threshold to trigger, what we can do is, I mean, this is why we have these, you know, circuits blocks here. If we just connect this charge outside, VDD here, maybe 2 resistors, RA, RB, and a capacitor, and connect the circuit like this. We can understand what will be happening here. I mean, you can just look at it. I mean, you have the chip here, right? You can, you know, connect this to a breadboard by just, you know, putting 2 resistors and a capacitor. Let's see what we obtain. Now, the circuit analysis, I mean, we'll assume that the reset is high. So this is high. If this one is high, this transistor will be off. Okay, so it will not be any effect on the circuit. So let's call this thing RB, maybe a small resistor. What happens? Okay, this looks a little bit complicated. By the way, what I said was wrong here. The threshold and trigger again are connected together, but that value is connected to V capacitor. So V capacitor is equal to Vin. So this is Vin, which is equal to V capacitor. Okay, because they are connected. Am I saying something wrong again? No. Trigger threshold is connected, yeah. Trigger connected, and then this is Vn, and then Vn is equal to V capacitor. Okay, so we have this Schmidt trigger action. So we can look at the operation in general, like how it's operating, and then we can calculate the time T1, T2, T3. Okay, so first, how we can understand the operation here. So we will keep in mind that with this kind of connection, that's what input output characteristic is. We can, you know, extract that again, but we don't need to because it's already done. So here the general operation. So what is happening when input is 0? So here for analyzing these kind of circuits, it's good to make an assumption like the capacitor is already discharged, okay? So capacitor is 0 volt. And we'll do one more assumption here. This collector emitter saturation voltage, instead of 0.2 volt, okay, so let's say it's 0 volt. It's just for simplicity, okay? For simplicity. Okay, so we need to maybe start analyzing this. The first thing we will do is assume that capacitor is 0 volt. So what is V out? How do we define V out? V out is this voltage, right? So V out is this. What is V out? You know, we can look at this circuit here. If the input is 0, V out is 0. So the input is 0 because the capacitor is equal to V in. If that is 0, V out is going to be 0. Okay, and notice that this V out is just following this voltage. Okay, so Q bar is 0, so output is going to be 0. If Q bar is 0, what is the state of Q2, transistor 2? So what is this value? That is going to be, input is 0, so it's going to be off initially. So in this period, Q2 is off. Okay. So if, you know, let's write the states of the transistors and other things here. For this region, if the input is 0, we say that S is equal to 1. Input is 0, so S is equal to 1. Reset is equal to 0. And then Q2 is off. Okay. And the current here, or the impedance here, is infinity. This impedance is infinity. This impedance is infinity. This impedance is infinity. Okay, so no current goes to the stages. This is off, so we will have the capacitor charging through here. Okay, so that means the capacitor initially at 0 will start charging. And what is the goal of the capacitor? The capacitor wants to go to VDD. Okay, so the capacitor wants to go to VDD. But the capacitor, you know, when it wants to go to VDD, what is capacitor? Capacitor is V in, right? So V capacitor is equal to V in. So until here, until V in goes to 4 volt, okay, nothing will change. The state of the circuit will remain same. And then this value, which is 4 volt, or let's write it 2 VDD divided by 3, capacitor will charge. And during that time, this will remain at 0. So this will be happening, and that's the goal of the capacitor, and to reach to VDD, but it really cannot. And what is the time constant here, tau? Any idea?
RA plus RBC.
Yes. So let's call this thing tau 1 because it will be maybe changing later on. So tau 1 is equal to C times RA plus RB. Okay. So, I mean, we know everything, so we can extract T1. What is T1? We can find that value, right? But right now we are just looking at the general operation of the circuit. So our goal is not to try to determine T1 right now. We will be determining that later on. So what happens if the signal reaches to, the input signal reaches to 4 volt? We know that at that time, you know, this signal will switch. So S becomes, I mean here, meanwhile, within this value, maybe I should say that S goes from 1 to 0, but nothing happens because it's stored its value. So here, S is 0, but R becomes 1, and therefore the signal starts switching. So when, you know, signal goes to 4 volt here, which is 4 volt here, okay, output will switch to VDD. So output will switch to VDD here and will remain VDD. Okay. So what about the transistor Q2? If output is VDD, then the, you know, Q bar is VDD. So Q2 becomes, you know, we select that RB small value, so it goes to saturation. Because a lot of current is coming here. So when it becomes SAT, this becomes SAT, and then output voltage goes to here, this voltage becomes what? What is this voltage? We collect the emitter of 2, and we said that is 0 volt, right? So it becomes 0. Interesting. So can it become SAT? I mean, we need to be sure that the current coming from here, which will go to this branch, is not too much, because then it cannot go to SAT, right? SAT condition was, what is SAT condition? Beta forward times I base of 2 should be larger than IC2. So we select the resistances and everything such that it goes to SAT. And then the SAT value, VCE2 SAT, VCE2 SAT voltage, we said it is 0 volt. That was the assumption, right? I mean, we assumed that VC SAT is 0 volt. So it's acting like a ground. So then there will be also current through here. I mean, there will be current through here. So we need to add them up. And IC2 is going to be equal to VDD divided by RA plus what? The maximum value of VC was what? 4 volts, right? So 2 VDD divided by 3 divided by RB initially. Okay. Or maybe I should write it maybe more formally. That value is equal to VC of T divided by RB. So VC of T will be changing, but the peak value, peak of this is equal to 2 VDD divided by 3, 4 volts. So we need to make sure that, you know, that RB value, this RB value, and then the circuit, you know, should be selected so that, you know, beta F times IB2 is larger than IC2, okay? So it's going to be maximum value of it. Make sure. So Q2 is in SAT. In some, you know, previous exams, you know, we selected the numbers maybe differently, or we ask you, you know, what should be RA, RB to make sure that they remain in the SAT. So, but you know, our concern is not to calculate things, right? I mean, we are trying to understand the operation. So as soon as output voltage goes to this, and then VCE2 becomes 0, okay, now the capacitor will start discharging. So C will start discharging. VC discharging. Here was charging, but now the condition changed and the capacitor will start discharging. What is the goal of the capacitor? To make the current 0. So then RB goes through RB. So the goal of the capacitor is to reach to 0. Okay. So it is trying to reach to 0. Okay. But things will change when? Things will change when the voltage coming here, coming here, coming here, the voltage goes to 2 volts. So when it reaches to 2 volt, 2 volts, things will change again. So this will go to 2 volts. It will be changing. Meanwhile, this goes while it's in here, you know, while the voltage decreases, this goes to 0, but nothing changes. I don't know. Am I saying something correct? Yeah. Oh, totally, yeah, that's true. Starts with R1 and R1, but the Q changes or doesn't change. Yeah, R1 changes, but Q doesn't change. So this will go to 0 again. So when this goes to 0, this will start trying to charge to VDD. And then things will change again when it reaches to 4 volt. And then it will be trying to go to 0 volt. So when it reaches to 2 volt here, things will change. So this was 4 volt, 2 volt. So then it will be going back again. So as you notice here, the T1, T2, and maybe T3 will be, what will be happening here. So what is the time constant here during this charge, this region? Remember, it was going and discharging through RB. So let's call this thing time constant T or tau2. Tau2 is going to be C times RB. So while it's charging, this is tau1. While it's discharging, it's going to be tau2. Okay. So now the capacitor, from the capacitor, we can determine the time periods here. So let's just carry that signal here. This will be increasing till here. So this is, let's say, 2 VCC divided by 3. And then it will be maybe switching here. And this is VCC or VDD, sorry, VDD divided by 3. And then it will be going back here and then going down again. So meanwhile, this will be going here, high, low, high, low. So the start of the capacitor voltage is known. This is known. This is known. Okay. And then the time constant wise, we know that here it's going to be tau1. This will be tau2, tau1, tau2. So this will be T1, T2, T3. And the period which will be repeating itself is going to be this. This is going to be T. And T is equal to T3 minus T1. Okay. So we know that, let's call this thing maybe time of X. This X will be equal to this X. And then if you say that this is maybe Y, this will be equal to this Y. Okay. So X is not going to be equal to Y because the voltages are, the target and initial voltages are different. Besides, time constants are different. So how can we determine this? So you will have maybe not equal signal. So duty cycle will not be 50%, but it's okay, like we can, you might play with things and then, you know, try to make the duty cycle equal to each other. How? Okay, if you want to cycle cycle to be 50%, then we can modify the circuit. I mean, this is maybe too early to mention, but we said that tau1 is equal to RA plus RB times C, and tau2 to be RB times C. Okay, so if we can make RB what can we do? While discharging, RB or charging RC. Yeah. We can do this. I mean, this is maybe it will be confusing you at this stage, but we can do this. We can do the charging through another resistor. And then the charging will be through here, RC. And then this charging will be through here with a diode. So if the ideal diodes are selected here, in this case, tau1 will be equal to RA plus RC times C. Tau2 is going to be equal to RB through C. So if RA plus RC is selected to be equal to RB, then 50% duty cycle is possible. And I hope it's clear. So while charging, it goes through here because this diode will be off. And then while discharging, it will be discharging through here. So RB is going to be the case. So here, assuming that the diode is on, is equal to 0 volt, for example. So it's possible to make the duty cycle 50%, but we will go back to the original circuit and do our analysis and then find time T1 and T2. So how can we find T1 minus T2? So what is this time difference here? So let's maybe write that here. So what is VC of T in this period? Maybe I should do this again, the original color here. VC of T in that period, okay? So during that period, we make it this color, and then this is the color. So this is what we are trying to find. What is happening here? This is initially 2 VDD divided by 2. And this is VDD divided by 3, sorry. And the goal, the final capacitor value is VC infinity is equal to 0 volts. Okay, so let's say this is T1, T2. VC of T in that period, okay, between T1 through T2, VC of T is going to be equal to V final plus V initial minus V final e to the power minus T minus T1 divided by tau. And which tau is that? Should be tau 2. Okay. So what is the final voltage? It is 0 volt. So this is 0 volt. And what is the initial voltage? 2 VDD divided by 3. And what happens when VC becomes T3? So sorry, T2. At that value, output becomes VDD divided by 3. And then this should be equal to initial value 2 VDD divided by 3 e to the power minus T2 minus T1 divided by tau 2. So from here, you can extract that the time, which is this time, x. Let's say this is x, okay? So, or T2 minus T1, which is equal to x, is equal to, it's equal to tau 2 ln 2. Okay, so you can do the same analysis for the next cycle. Let's say the red cycle. What about between T2 to T3? What is VC of T? VC of T is equal to, again, V final, V initial minus V final, and then e to the power minus T minus T2 divided by tau 1 this time. So what is the final value here? It's trying to go to VDD. So this is VDD. What is the initial value? VDD divided by 3, and the final VDD. And then what happens when VC reaches to T3? And that time, you know, the output voltage will reach to 2/3 of VDD. And then, you know, if you write the equation here, VDD plus or minus 2 VDD divided by 3 e to the power minus T3 minus T2 divided by tau 1. And if you look at this, the output, interestingly, again, going to be it's going to be again y value, which is this is y. This is called y, which is equal to T3 minus T2. It will be equal to tau 1 times ln2. Okay, so if we look at then t, total t, which is T3 minus T1, it's going to be ln2 tau 1 plus tau 2. Okay, and then what is the frequency? It's 1 over t. So this is an interesting result. So we can set the frequency of operation here and make it and set it up according to what we want. And again, like if this is you really require 50% duty cycle, then you can do some other tricks. Any questions here? I guess the time is up.
Hocam benim bir sorum olacaktı. VC satı biz 0 kabul edince sanki
Evet.
discharging RC pet üzerinden oluyor gibi oldu ama aslında değil. O nasıl etkiliyor normalde operasyonu?
No, I mean, here, let me try to show the screen again. Remember the model for the transistor. Where can I show it? Maybe I should show it somewhere around here. Okay. The model for saturation is like this, right? So this is 0.8 volts, and then this is a voltage source, right? So instead of saying 0.2 volt here, we say it is 0 volt. Okay, so it's going to be ground then, like, you know, this is ground, and this is also 0 volt. Is that clear?
Anladım. O
So
yüzden saturation
no
olmasını
matter,
istiyoruz.
yeah, no matter how much current goes through, it's going to be 0 volt. Okay, but of course, I mean, as long as this situation is satisfied so that the transistor is in saturation. Okay.
Anladım hocam. Teşekkürler.
Okay. Good. Thank you for asking questions. Otherwise, I feel alone here. Okay, let me stop recording.